Hello everybody! Today I present you our highly parallel linear forest extraction from a weighted graph on GPUs, and this work was done by myself. I'm Christoph Klein, and my PhD advisor, Professor Dr. Strzodka at the Heidelberg University at the Chair for Application-Specific Computing. So, why do we want to extract linear forests from graphs? So they can be used, for example, in directional coarsening in multigrid methods, or in adaptive algebraic smoothers, and also something we show in the paper, they can be used to construct algebraic tridiagonal preconditioners. So what is a linear forest? I show here, we see here two definitions. A linear forest can be a union of disjoint paths and also an acyclic 0-2 factor. And this definition is more relevant for this talk because we compose the linear forest computation into two steps. So at first we compute the 0-2 factor, and then we make it acyclic. So the next question is, what is a 0-2 factor? And to understand that, we start with a 0-1 factor, and I show you here a 0-1 factor in this graph. So for example, 1-0-1 factor here would be this. So every edge which is marked in blue is part of the 0-1 factor, and this is pretty well known, and in literature you can find a lot about this when you search for graph matching techniques. And in a 0-1 factor, every vertex is allowed to have between 0 and 1 edge. And in a 0-2 factor, every vertex is allowed to have between 0 and 2 edges. So for example here, vertex 2 has 2 edges, but vertex 6 only 1, because it cannot have more, because vertex 1 already has 2, vertex 2 also already has 2 edges, so these cannot be part of this 0-2 factor. Yeah, and we can continue here and add more edges, and we can make, from this we can create a 0-3 factor, which for example is this one, or a 0-4 factor, which finally now includes all edges of this small example graph. So these are these 0n factors. So, but often in practice you have not just a connected graph, but you also have weights on the edges, which I marked here by using thin and thick lines. And our objective here in these weighted graphs is, so we want to compute a 0-2 factor including these strong weights. And how do we do this? So in parallel, for each vertex, we can now propose along existing strong edges in this weighted graph. So for example here, vertex 6 proposes to vertex 2 and to vertex 5, because the edge to vertex 1 has a smaller weight. And for the other vertices we do it in the same fashion. So each vertex takes its two strongest edges and proposes along these strongest edges. So in the next step, then we confirm mutually proposed edges. So for example here, 3 proposed to vertex 2, 2 to 3. So now we say these edges are part of the 0-2 factor. And here we only have one proposition, so nothing is confirmed here, and this edge is not yet part of the 0-2 factor. Yeah, we can do this iteratively. So right now here I'm also marked the vertices which already have two confirmed edges. That's the maximum amount of edges. So they won't participate in any proposition anymore. And also, no vertex can propose to them anymore. So vertex 7 cannot propose to 8 because 8 already has two edges. And this is what we see here. Vertex 6 can only propose to 1. 1 potentially can propose to 6 or to 0, but vertex 1 can only propose one edge because it already has one confirmed edge, so it cannot propose along two edges anymore. This is what happens here. Yeah, and here the same, 3 and 7 also can only propose one edge, and they do it to each other. So yeah, let's confirm the mutually proposed edges again, and yeah, then we see this is now the final 0,2 factor. Vertex 6 hasn't got any edge here, and yeah, this is something which can happen with this technique. So this would be the final 0,2 factor. Yeah, but the interesting part is now the implementation, because for a trivial implementation, one would use one GPU thread for each vertex. But that is not good for load balancing on the GPU, so we had a more detailed look into that, and it turns out so you can formulate this as a sparse matrix vector product actually, with generalized multiplication and addition operators. So here you see this sparse matrix vector product, and A represents the adjacency matrix, so the graph essentially, and Y represents the proposed edges, and X the confirmed edges. So to understand this, why is this a sparse matrix vector product, we have a look at the very first proposition of this iterative proposing process. So and each vertex proposes to its along its two strongest edges. So we must find in this adjacency graph, we must find the two strongest coefficients and where they come from. So we need to find the column indices of these two largest values in each row. And yeah, a sparse matrix vector product is nothing else than a reduction along these matrix rows. So let's do this together for a 0,2 factor. So what we see here with Aij, these are the matrix values, and for sparse matrices we save the column indices for these coefficients, and now we start doing this reduction along this row. And yeah, we have a more complicated accumulator type for this because we need to find the two largest values, and also we must keep track of their column indices. So we start here with the first value. We put this value 1.2 and the column into the accumulator. The second value is not set yet. So then we go to the second value and we insert this, and since the 3.4 is larger, it goes to the top here, and we also carry the column index here. And now the next large value is found, and we must insert it in the accumulator, and we see that the 1.2 just drops out here because it's smaller. Yeah, and in this fashion we continue. So 3.6 is also inserted, but on the second position here. And yeah, then we insert the 9. This value is too small, won't get inserted. And yeah, in the end, so we found the two largest edges for this vertex I, and that's from vertex 9 and vertex 5. Yeah, so let's have a look at the performance of this zero n factor computation. Here we see part of the results in the paper, and on the x-axis we see matrices from the sparse matrix collection, which are very large, so more than 1 million vertices, and on the y-axis we see the relative kernel time, so this time is relative to the slowest scheme. So the slowest scheme is always at 100%. And for comparison, just as roofline, we also have a look here at a normal sparse matrix vector computation. So the schemes here, they don't calculate the same thing. So here we see the sparse matrix vector computation from sparse, and then the brown result is from our sparse matrix vector kernel. And we use this sparse matrix vector kernel, which is written in a very general way, such that it can process arbitrary addition and multiplication operators. So this sparse matrix vector code is also able to compute these zero n factors with appropriate user-defined operators. And this is what we see then for the next 4 bars here. So here we see the proposition for 0, 1 factors, for 0, 2 factors, 0, 3 and 0, 4. And they consume much more time, but they also do much more work. So the kernels consume much more work, just as the reduction along the matrix row needs more operations, and that's the reason why of course it has to take more time, but nevertheless it's so for example here it's 3 times the time of the normal space matrix vector product, but for the complexity of operations this is still a good result. So, and yeah, what does this actual result then look like? So what is the output of this 0,2 factor computation? That is a vector of confirmed edges. So for example here we have vertex 0, and vertex 0 has a confirmed connection to vertex 1 and 2. And of course then vertex 1 needs to have a confirmed connection to 0, and here to 9, and the next one to 127 and to 0. This is the vertex 2. But it can also happen, as we saw, that some vertices, they might only get one edge or no edge, and yeah, we can mark this with a -1. And this structure is like a double linked list. So the question is now, how do we find cycles? How do we break them up? How can we compute path ID for each vertex? So we would like to know what is the ID of the path the vertex is located in or part of. And also we want to know what's the position for each vertex in its path. And we have to get this from this double linked list like structure. And the solution to all of these questions and problems is we can use the bidirectional scan technique for that. So this is looks like this. So here we see on the lowest level we see the vertex IDs, so vertex 0, 1, 2, 4, 9, 8 and so on, and the green line connects now vertices which are in the same path, so they have a confirmed connection to each other. And now we want to find the path ID, which we can define at the minimum ID of the path ends. So for example, for this path from 4 to 7, the path ID would just be 4, and here the path ID would be 1, here it would be 0, here it would be 6, because they are just they don't have a path, they are just these vertices are alone. So we need to exchange this information somehow, and where is the path end, what's the ID of the vertex at the end, and this can be done by this bidirectional scan, which operates on this double linked list structure. So in the first step, we visit our next neighbors, the plus minus 1 neighbors here. And we check, are you a path end? And if so, I have found it. Great. And let me exchange that with my 2-step neighbors in the next scan step. So this is then the next actual kernel launch on the GPU. And here you see now we visit the neighbors which are more far away. And in the next kernel launch, we visit the plus minus 4 neighbors. And so on. So this distance of neighbors we visit, it grows exponentially. And yeah, in that way we have a logarithmic amount of kernel launches for a certain amount of vertices. Yeah, let's have a look at the performance of that. So what we see here in the plot, in the upper plot, is the throughput in gigabytes per second on a GPU, on the RTX 2080 Ti. And yeah, here we cannot just show the throughput because we have many kernel launches with an irregular access pattern. So we show these box plots here. And as a comparison, we show here the copy kernel, which is essentially just a stream benchmark. So it gives us an estimate about the memory throughput limit. And yeah, we use this bidirectional scan to identify the cycles or to identify the paths. So find path ID and the position of each vertex within a path. For performance reasons, we use 2 different kernels from that for that. And yeah, here the message of this plot is we are close to copy kernel performance. We cannot reach it because of irregular memory access, but we are far away from low performance. So what you see here is 400 gigabytes per second. Here's 500. So this performs rather good. And in the lower part of the plot, we see on the x-axis again the same matrices from the space matrix collection. On the y-axis the time in milliseconds, and we compare this GPU solution with the sequential CPU solution. So yeah, the CPU solution here, it has much less work. It only has to traverse this data once, but nevertheless, so although the GPU algorithm here does more work, it's much faster here. So here in black we have the speedups varying from 23 to 13. Yeah, so this solved here our problem. Yeah. And as a summary, I want to highlight again the techniques we used to extract this linear forest. So we used our generalized sparse matrix vector product for this 0n factor computation, which could be executed efficiently for up to 0.4 factors. For larger factors, we have to use different techniques, but that's future work. And yeah, the bidirectional scan is very well suited for these double linked list structures, and you can use it in graphs for cycle detection, for finding weakest edges in a cycle or path. You can compute the overall path ID and or the position of each vertex in a path, and so thank you very much for your attention, and now I'm looking forward for questions.